We now move on to the analysis of stresses. Before getting deeper into the stress analysis, it is important to mention that the analysis of strain, which was done previously, and now the analysis of stresses, both are applicable to any material body that can be treated as continuum. So, by continuum, we mean that the body hasn't got any gaps inside, or it hasn't got any cracks, or it's not damaged anywhere. So it's a continuous body, which means to say that we can resort to vector calculus for analyzing the body. During the strain investigation, we discussed that in the continuum mechanics approach, the method of cut is normally used. In the method of cut, a body is imagined to be cut into two parts. One part is discarded, and its action on the remaining part is considered. The actions include internal forces, moments, etc. So imagine we have got this continuum potato, and in this body, we have it subjected to different types of loading. We cut this body by a cut plane, which is called as a cut plane P over here. This cut plane divides the body into part A and part B. If we want to consider only one part of the body, then we will have to apply the effect of the other part of the body onto the considered part of the body. And this is in accordance with the Newton third law, that is, every action has equal and opposite reaction. In the analysis of stresses, there are some other definitions which are required, and let us go through them one by one. The first definition is a free body. A free body, or a small element of a body, is imagined to be cut from the material and free from remaining part, with the external forces acting on that element. So, if we consider part A as our reference body and we decide to omit part B, then part A is our free body. In the case of free body, we have to make sure that the influence or the effects of part B are applied onto part A. Thus, we can say that the internal interaction acting on the surface of the free body before cut are replaced by forces distributed over the whole surface of the free body after cut. The other definition involves plane. A plane can be defined by its location and direction. For example, we have got this cut plane P, which is located at a particular position within a body, and this plane has got a direction shown by an outward drawn normal. The plane P cuts the body into two parts, A and B, without losing generality, is given to the free body B only. Therefore, the boundary of the free body B is shown by the solid lines. Plane P is defined by its location at point Q, together with its direction defined by the unit normal n. It is to be noted that the cut plane P has two sides, one with each part of the body A and B. One side can be considered as arbitrarily positive, whereas the other side can be considered as negative. So that depends on what sort of sign convention we want to apply. The next definition, which is very important, that is of body force. The body force represents force per unit volume. The example of a body force can be self weight of a body which acts at a particular point and which can be shown by some force by volume. Similar to body force, we have got surface forces. These are distributed loads which are applied onto some area. So we can see that there is a distributed force which is applied on this body. They are normally shown by force per unit area. The example can be hydrostatic forces or retained soil. This brings us to stress notations. As discussed, we normally use the free body diagram to specify the state of a stress at a point and to obtain relation between various stress components. In general, a free body diagram can be a box-like volume element of member. The loads which act on these free bodies are either the surface forces, which, as we discussed, are forces that act on the surface of the free body, or body forces that act throughout the volume of that portion of the body considered. Please note that the example of a surface force can be a contact force. So when we say that the surface force is applied onto our plane, cut plane, after omitting a portion of the body, that means that a contact force has to be introduced into the onto the cut plane. These contact forces are actually surface forces. The free body diagram of a box-shaped volume element is shown in this figure. This figure is drawn in a 3D Cartesian system, and we have stresses appearing at each and every face of the cube. In this figure, the volume element is shown to have a corner at origin, which is named as point O. We assume that the stress components are uniform or constant throughout the volume element. In the case of this volume element, the surface forces can be represented by stress component and the areas on which they act. So we have got these faces, and all these faces have got at least 3 stresses in distinct directions. And all these stresses can be multiplied with the respective area of the surface or the face to get the surface force. Similarly, this volume would have some body force, and that body force would be represented by the product of the components and the volume of the element. So the body force in the x1 direction can be considered as, say, B1 times the volume of the element. The body force in the x2 direction can be considered as B2 multiplied by the volume. And similarly, the body force in x3 can be considered as B3 multiplied by the volume. Please note that higher order terms are not shown in this element. In the case of this volume element, there are 2 faces that are perpendicular to x1 axis, 2 faces perpendicular to x2, and 2 faces perpendicular to x3 axes. The face whose outward drawn normal is in the direction of positive x1 axis is the positive face, and the face whose outward drawn normal is in the opposite direction of x1 axis is the negative face. The same argument can be applied for x2 and x3 faces. The stress component on the positive x1 face are sigma 11, sigma 12, and sigma 13. Their positive sense is shown in this figure. Please note that in accordance with the Newton's third law, the positive stress components sigma 11, sigma 12, and sigma 13 acting on the negative face are in the negative x1, x2, and x3 directions. Therefore, a positive stress component sigma 11 exert a tension or a pull parallel to the x1 axis, and equivalent sign conventions hold for the planes perpendicular to the x2 and x3 axes. In the case of the volume element, we have 6 faces. And if every face has got 3 stresses, then we can say that altogether there are 18 stresses of the element. These 18 can be reduced to 9 components because of Newton's third law and equilibrium. The 9 stress components may be further reduced to 6 for most practical problems. The 9 stress components relative to x1, x2, x3 coordinate axes may be tabulated in an array form as shown over here. Symbolically, T represents the stress array called stress tensor. In this array, the stress component in the first, second, and third row act on planes perpendicular to x1, x2, and x3 axes respectively. Thus, as discussed, 9 stress components are required to describe state of stress at a point in a member. However, if only forces that act on the free body in the figure above are surface forces and body forces, we can demonstrate from the equilibrium of the volume element that the 3 pairs of shear stresses are equal. So let us go to the figure above. So from this free body diagram, if we take moment above x3 axis, we will get sigma 1 2 times the area of the face that is normal to x1 axis times the lever arm dx1 must be equal to sigma 2 1 times dx1 times dx3 times the lever arm dx2. The summation of moment about x3 will result in sigma 1 2 equal to sigma 2 1. So sigma 1 2 on the positive x1 face can be changed into force by applying the area of the face, and then the lever arm can be multiplied to get the moment, which is counterclockwise according to right hand rule. This counterclockwise moment will be resisted by sigma 2 1 on the positive and negative face along x2. Thus, we get sigma 1 2 equal to sigma 2 1, sigma 1 3 equal to sigma 3 1, and sigma 2 3 equal to sigma 3 2. Hence, for this type of stress theory, only 6 components of stress are required to describe the state of stress at a point in a member. Now, let us determine the stresses acting at arbitrary plane. The stress vector sigma 1 on the plane that is perpendicular to x1 can be written as sigma 1 1 x1 plus sigma 1 2 x2 plus sigma 1 3 x3. We can see that along x1 we have 3 components of stress. A similar argument can be made for sigma 2 and sigma 3 on the planes that are perpendicular to x2 and x3 respectively. Hence, sigma 2 is written as sigma 2 1 x1 plus sigma 2 2 x2 plus sigma 2 3 x3, and sigma 3 is written as sigma 3 1 x1 plus sigma 3 2 x2 plus sigma 3 3 x3. We can also look into this figure and see that at the faces which are perpendicular to x1, x2 and x3 will give us sigma 1, sigma 2 and sigma 3 accordingly. Now consider the stress vector sigma p on an arbitrary oblique plane P through point O of a member. The unit normal vector to plane P is given as Lx1 plus Mx2 plus Nx3, where L, M, and N are the direction cosines of the unit vector N. Let the area of triangle BNC is A. Then the area of the face perpendicular to x1 will be AL 2x2 will be AM and 2x3 will be AN. Thus, using the equilibrium, we can write that stress sigma P times A, which is the area of the plane of interest B and C, is equal to sigma 1 times AL plus sigma 2 times AM plus sigma 3 times AN. Please note that A is multiplied with sigma to get the equation in force. Let A be the area of triangle ABC, then the area of triangle ABO face whose outward drawn normal is in the direction of x1 is A times L. Similarly, area of the triangle OBC, which is perpendicular to the x2 direction, is A times M, and area of the triangle OAC, which is perpendicular to x3, is A times N. Thus, using the equilibrium of forces, we can write the equilibrium equation in vectorial form as sigma P times A is equal to AL times sigma 1 plus AM times sigma 2 plus AN times sigma 3. Please note that sigma is written in vectorial form. From this, we can write that sigma P is equal to L times sigma 1 plus M times sigma 2 plus N times sigma 3 because A get cancelled on both sides. We can also write sigma P as sigma P 1x1 plus sigma P 2x2 plus sigma P 3x3, i.e. sigma P can be decomposed into three components along x1, x2 and x3 directions. Sigma 1, sigma 2 and sigma 3 in this equation can be replaced by the corresponding equations shown over here. And after that, we can compare the coefficients of x1, x2 and x3. By doing so, we can get the components sigma p1, sigma p2 and sigma p3 as L sigma 1 1 plus M sigma 2 1 plus N sigma 3 1. Sigma p2 will be equal to L sigma 1 2 plus M sigma 2 2 plus N sigma 3 2, and sigma p3 will be equal to L sigma 1 3 plus M sigma 2 3 plus N sigma 3 3. After finding out sigma p, which is the stress at the reference plane whose outward drawn normal is in the direction of capital N, we can find the component of the stress in the direction of normal to the plane. That is done by taking dot product of sigma p with the normal vector of the reference plane. That will give sigma pn equal to L square sigma 1 1 plus M square sigma 2 2 plus N square sigma 3 3 plus 2mn sigma 2 3 plus 2ln sigma 1 3 plus 2lm sigma 1 2. Similarly, we can find the shear at the reference plane by using Pythagoras theorem. Thus, we can subtract sigma square pn from the magnitude of sigma p square and take the square root to find out the shear appearing at our reference plane. In this way, our sigma p can be decomposed into two components, one normal and another one shear component on the area ABC.